This is Jonathan Gardner. We're doing section 4.31 of Griffith's Introduction to Electrodynamics, second edition. I'm going to go fast, but you can rewind and replay. If you like what you see, you can like it and share it with your friends. And if you have any questions or comments, you can put them in a response video or in the comments below. And, well, let's get started. So now we're going to combine. We know that when we put these dielectrics into an electric field, they polarize. We know that a polarized dielectric produces an electric field. Accordingly, you know, that behaves with the bound charge density according to the divergence of the polarization and the surface bound charge, and the bound charge surface density being according to the polarization dot the normal vector of the surface. And we discussed that these are actual charges, they're real, right? So the problem usually is that we introduce free charges, some free charge density, and so we get the actual charge density is equal to whatever bound charge we have, this is within a dielectric, plus whatever free charges we've added, okay? And so Gauss's law basically says that the divergence of the electric field is equal to the charge density over epsilon naught. Well, now we have that. So we have the divergence of the electric field, epsilon naught, the divergence of the electric field, is equal to the bound charge plus the free charge. Okay. And the free charge is equal to the divergence, negative the divergence of the, the bound charge is equal to that. So let's write this out this way. So this is, let's use this equation here. So minus the divergence of the polarization plus whatever free charge we've added. And so we combine terms. We have epsilon naught, the divergence of E, plus the divergence of P equals the free charge. And we can draw out this, the divergence of, that gives us the free charge. Now this term right here, we're going to call this the electric displacement D vector. Okay, so that's just epsilon naught times the E vector plus whatever polarization happened in the dielectric that we're looking at. And so in terms of Gauss's law, the divergence of this D vector is equal to the free charge, right? So we basically bypassed whatever the polarization would give us in terms of bound charge, and when we know this D vector, we can just go straight to the free charge. If we know the free charge, we can find what the D vector is supposed to be. Rewrite that in integral form. We have the surface integral of the D vector dot the dA vector of that surface is equal to the total charge of the free charges enclosed. Okay, so let's put a box around these two dudes. This is Gauss's law in displacement, and this is Gauss's law in integral form for displacements. Now let's talk a little bit. Oh, this is also important. Okay, the actual charge is equal to the bound charge plus the free charge. This is useful because oftentimes we have a dielectric configured in some way, and then we're introducing a free charge, and that's going to cause, you know, some surface bound charges, some bound volume charges, and we don't really know what, and we want to solve the problem anyway. So looking at D means that we can kind of ignore what's happening with the stuff on the inside. Now, moving right along, let's do example 4. So example 4. A long straight wire carrying uniform line charge lambda is surrounded by a rubber insulation out to radius r. Find the electric displacement. So we have lambda, a long wire, for all purposes it's infinite, and it's surrounded by rubber insulation of radius r. Okay, and so we want to find the electric displacement D vector. Okay, So we're going to draw a Gaussian surface on the inside there. We're going to use Gauss's law for displacements. So let's use something like this. Distance L, radius little r. Okay. And so Gauss's law for displacements is that the integral of the d vector dot the area vector is equal to the free charge enclosed. So that would give us, the free charge is lambda, right? So lambda times the distance L. Now, because the infinity, these two little bits aren't going to matter, it's only the surface of that cylinder. So the area of that cylinder, the d vector, isn't going to vary. So we get d times the area of the cylinder, which is 2 pi rl, is equal to lambda L. Okay, and so d is equal to lambda over 2 pi r. And which direction is that pointing? It's pointing in the r hat direction. Okay. So notice that even if you move outside, if you expand this this thing to the outside, then you still can work in the outside where there's no dielectrics. We know that the P is the polarization is going to equal 0, and so the d vector, if you recall, is equal to epsilon naught times the e vector plus the p vector. Well, on the outside, if we expanded this to we're on the outside now, this p vector goes to 0, so we get e vector on the outside is equal to lambda over epsilon naught 2 pi epsilon naught r in the r hat direction, where r is greater than the radius. Okay, so we can calculate the electric field on the outside there, and it's kind of interesting that it has nothing to do with the how the charge is allocated on the inside, which I guess wouldn't surprise you, because you know that insulator doesn't carry a net charge, and so the net charge is only whatever is enclosed by that line. Inside the rubber field, we can't calculate the electric field unless we know the polarization, and we don't really have a way to calculate the polarization. We can't use this to calculate what the surface charge would be, the bound surface charge along this insulator would be. The reason why is, as you basically we have to reconcile this with that, and so there's this jump that has to happen, and that jump is because the bound charge, suddenly has to go from something to nothing, and so every else, we just can't calculate it right at the surface. And if you wanted to think of it as, the insulator has some finite thickness on the edge there, then you can have the bound surface charge would vary more smoothly with that, and you can use Gauss's law everywhere. But unfortunately, we can't do that. Anyway, but the integral form, when you use the integral form, you're only counting the charge inside. You don't worry about how the differential actually behaves at these weird boundaries where things blow up. So it works out in the end. Hope you enjoyed that. Thanks for your time. Bye.